Here my circuit is running the blink code. You can see the LED is flashing 1 second on and 1 second off, connected to pin 13 and a 330 ohm resistor. Here I have the working code for blink faster. In this code, the length of the delay can be altered by the user by changing the variable delay length. Currently, this is a delay length of 100 milliseconds. If I change this to 50 milliseconds, you'll see that the LED is blinking faster. If I change this to 15 milliseconds, you'll see the LED is blinking so fast that we can just barely see the blinking pattern of the LED. If I change this to 10 seconds, it's blinking so fast that we can't even make out the change in the LED. Here's the working code for the fade function. The fade function scales between brightness levels at a rate of 5 brightness levels every single loop iteration. These brightness levels each correspond to a different duty cycle. So you can see that at the seemingly low brightness position, the duty cycle favors off over on. At the high duty cycle, the high brightness, the duty cycle favors on over off. And you can see this function is constantly scaling between duty cycles. Higher duty cycles means brighter LED, lower duty cycles means dimmer LED. Here's my working code for number 4, rewriting the fade functionality with digital writes instead of analog writes. This is the fast fade. You can see that it scales between brightness levels rather quickly with only 1 loop per duty cycle. If I change this to 2 loops per duty cycle, I get a medium fade. So every single duty cycle, the code is looping on and off for 2 full cycles on each duty cycle. If I make this 3, it's even slower. We get our slow fade functionality. Now all of these fade functionalities are at a frequency of about 500 hertz, or a duty cycle period of 2,000 microseconds. I can change this 2,000 microseconds to be, say, 1,000 microseconds and double the frequency of the duty cycle. This is another way of changing the speed. So now if I make it 1,000 microseconds, even though I'm looping 3 times like I was in the slow, you see I'm going so much faster because my period of duty cycles is shorter. There are a couple of advantages to using our custom PWM rather than the built-in PWM functionality of the Arduino Uno. Notably, our custom PWM allows us to change the frequency of the pulse width modulation duty cycle. Using the built-in pulse width modulation, we are forced to use a duty cycle with a frequency of 500 hertz. But in our custom application, we can change that frequency of 500 hertz to be higher or lower depending on how we want our duty cycle speed to be affected. However, it's a lot less clean in terms of code, and it's a lot less understandable on the part of the user. Having a fixed PWM on the Arduino Uno makes it pretty universal when modifying the DAC digital analog converter, and it can be neatly done, as we saw in the first fade functionality, in 1 analog write. So it's really a debate between cleanliness and versatility. Here I've got my custom application. I designed a electronic dice roller. You'll see the LEDs are arranged in the formation like the pips on a die. And every single time I call a function roll dice, it randomizes a roll from 1 to 6 and lights up LEDs corresponding to that roll. So for example, right here, it rolled a 3. If I look at my monitor, it says roll equals 3, and we saw that 3 LEDs were lit. Now I got a roll of 5. 5 LEDs are lit. Roll of 4. You'll see the monitor says roll equals 4.